In this video, we're going to actually look at a special example and then we're going to generalize from the example. I would like you to start by making the addition table for Z mod 6Z. And what I want to remind you of is that the elements of the ring Z mod 6Z are the 6 distinct cosets of the subring 6Z inside of the ring Z. So stop the video and make that table. And once you have it, start the video back up. So hopefully you did that. Here is my table of values for this particular addition table. And what I want to notice is that if I look at just the representatives of each one of these cosets, the table looks awfully familiar. We start by underlining these guys. Some of them were already underlined. Let me finish underlining the ones that weren't underlined. And when we stare at these representatives of all of these cosets, we start to realize that this particular addition table looks an awful lot like the addition table for the integers mod 6. And the integers mod 6, remember, are just the set 1, 2, 3, 4, 5, where we do the addition and the multiplication modulo 6. Okay, what I want to do next is I want you to do the same kind of thing for the multiplication table. In other words, I want you to do the multiplication table for Z mod 6Z, where again, the names of the 6 distinct cosets are going to be these names. So stop the video and find out the multiplication table for Z mod 6Z. And hopefully you've done that. And when we look at this, the table looks like this. And again, if you look at these representatives, this starts to look an awful lot like the times table for Z6. And I do kind of want to illustrate what I mean by that. So let me focus my attention on something like 4 plus 6Z times, I don't know, maybe this one, 5 plus 6Z. Well, we would think about that as being 20 plus 6Z, but 20 plus 6Z is the same as 4 plus 6, not 4, 2 plus 6Z. Since 20 minus 2 is equal to 18, and 18 belongs to 6Z. And sure enough, if I look at this particular entry, 4 plus 6Z times 5 plus 6Z is indeed that particular element. Now, we already know that if two rings have virtually identical addition tables and multiplication tables, if the tables are identical except for the names that we're giving the elements, the two rings are isomorphic. So this raises the question, is Z mod 6Z isomorphic to Z6? Now, what I basically have to do is I want to think about trying to come up with an isomorphism. So, and there's an obvious kind of a candidate. I'm going to let phi act on the left cosets by simply being equal to A mod 6, where I'm thinking about A mod 6 as being a proper element of the ring Z6. In other words, if A is actually not in the set 0, 1, 2, 3, 4, and 5, I know that A plus 6Z is the same exact left coset, named C plus 6z. Let me say that much more clearly. I know that A plus 6z is equal to C plus 6z, where A and C are congruent mod 6, and C does belong to the set of elements inside Z6. And I also know that when this happens, that A minus C is some multiple of 6. So what this basically means is that when I'm looking at my rule, and this can be how my rule can be stated, that phi of A plus 6z is going to be equal to C, where A is congruent to C mod 6. This says that I can actually build an explicit table of what the phis are. So I'm going to look at a table of values for the phis. The first thing I'm going to do is I'm going to write my elements of Z mod 6z. And they are 0 plus 6z, 1 plus 6z, 2 plus 6z, 3 plus 6z, 4 plus 6z, and 5 plus 6z, and any other left coset inside this ring is equal to one of those elements. And now I'm going to think about, what does phi do? Well, phi takes this one to 0, and phi takes this one to 1, and phi takes that left coset to 2, and phi takes this left coset to 3, and phi takes this left coset to 4, and phi takes that left coset to 5. And if you look at this, phi is obviously both 1 to 1 and onto. So the only real question is phi a homomorphism? Well, to investigate that, what we're going to have to do is we want to think about whether or not phi preserves the ring operations. So does phi preserve the ring operations? Well, to do this, I'm going to basically again set up some notation. If I let A plus 6z and B plus 6z be inside Z mod 6z, then I know that A plus B plus 6z is going to be equal to, let's call it C plus 6z, where C is indeed inside 0, 1, 2, 3, 4, or 5, and A plus B is congruent to C mod 6. In other words, I know that 6 divides A plus B minus C. And since I know this, that will imply that. And now all I have to do is think about what happens with phi and how phi behaves on the sum of A plus 6z and B plus 6z. In other words, I want to look at this. So under all of these pieces of knowledge, I want to look at this. Phi of A plus 6z plus phi of B plus 6z is going to be A plus B mod 6. And that's by the definition of phi. But A plus B mod 6 is just equal to C, because we just got done establishing that these two things are the same. And C is phi of C plus 6z, But that is also equal to phi of A plus B plus 6C. And this is because 6 divides A plus B minus C, which means the two cosets are the same. Well, so now the question is so what we now have is that phi does preserve addition. So now the question becomes does phi preserve multiplication? And again, what I'm going to notice is that A times B is congruent to something. I'm just going to call it D, mod 6, where D belongs to the set 0, 1, 2, 3, 4, and 5. And when we look at this, then what I can say is the following. Phi of A plus 6Z times phi of B plus 6C is just going to be A times B mod 6 by the definition of phi, but that's going to be D, and D is going to be phi of D plus 6Z, but D plus 6Z is the same thing as AB plus 6Z. And that is again since 6 divides AB minus D, because we've already specified that AB and D are congruent mod 6. And hence, phi does preserve multiplication as well. And so what we do have is that phi is a ring isomorphism. It is a ring homomorphism, and we've already seen that phi is 1 to 1 and onto. And hence, phi is a ring isomorphism, and Z mod 6Z turns out to be isomorphic to Z6, the integers modulo 6. Well, there's nothing special about 6. So what I want to do to tie this thing up is an observation. The same kind of proof can be written to show that Z mod NZ is going to be isomorphic to Zn, where the isomorphism is given by this formula. So phi is going to take the left coset A plus n times Z, and it's just going to send it to whatever A is mod n. That will be a ring homomorphism, and it will be 1 to 1, and it will be onto. And hence the two rings are isomorphic. And that concludes this particular video.